also the magnetic signatures. So I'm an experimental physicist, as Manoj has just mentioned. So from that point of view, I'll try to, what I've prepared is, what I've thought is that the audience is possibly diverse, and based on that, and because of that, I'll try to give some overview about few different kind of materials which are possibly which are kind of interesting, and which are being looked at the magnetism groups worldwide. And in the second phase of this lecture, I will try to give you some experimental ideas how to measure those signatures of magnetism or quantum magnetism in this kind of materials. So before I start, I'd just like to give a brief introduction about my research group, what we are doing. Here, so this slide is a little bit old, but primarily these are the kind of different materials, different kind of physics that we are exploring at IIT Delhi. So magnetism is one good part of that, where we are looking at magnetic fermions. I will give a brief introduction about that. We are looking at artificial spin ice. Also, I'll briefly introduce. The lecture being of 1 hour, it will not be possible to go too much deeper into these materials or the problems, but at least there will be some introduction about those materials. And also recently we have started working on the van der Waals magnets, 2D magnetism. So that also I'll touch on during this talk. Additionally, we are also working with a very nice system that we have established at IIT Delhi, which is ultra low temperature, ultra high vacuum scanning tunneling microscope, and where you can do actually atomic resolution images. We can go down to the system is capable of going down to 330 millikelvin with magnetic field, vector magnetic field of 2 by 2 by 9 Tesla field. One can do atomic resolution, then high resolution imaging, and then high resolution spectroscopy, tunneling spectroscopy. This DIDV is actually proportional to the local density of states. So basically, you can look at the local density of states of different metals, metallic systems, semiconductors, etc. So we are working heavily on using that equipment. So this system is actually is a central part of a centralized facility at IIT Delhi. So that means that it is possible to book the system online, also by the anyone within the country can book it online, and then one can perform measurements on payment basis. So if there is any question on this, I'll be very happy to answer. Currently, I'm coordinating this effort at IIT Delhi. So if there is any question, we'll be happy to answer. Yeah, so this is one, I think, nice image. Sorry, the spectroscopic data is missing somehow. But what you see on the right side, on the left side is a material called niobium diselenite, which is a superconductor below around 9 Kelvin. And we have measured actually the conducting vortices using that STM at 330 millikelvin, which is on the right side of this of your screen. So these are kind of the measurements that you can do, and as I said, we are currently working on this. So this is the plan of the lecture. So which is about different magnetic quantum materials. So as you see, the list is pretty heavy. So one can start. I'll start with these frustrated magnetic materials. But due to the time, I'll just touch upon only 2 to 3 different materials. So these are highlighted here. So frustrated materials, quantum spin liquids, skyrmions, and 2D magnetic materials. Right, so I believe that some other expert will be talking on these topological magnetic materials, heavy fermion magnets, etc. Okay, so I'll start with the quantum spin liquid. I'll skip this slide and let me start with this. So all of us in our daily routine we experience some kind of frustration in work or otherwise, right? So I think a little bit of frustration is interesting because otherwise life would be boring. Once you solve the frustrating problem, then actually there is some kind of enjoyment that you get, and actually that possibly drives you to look at things more challenging things. So let us talk about frustration physics. So it is, I'm not talking about the frustration in workplace, but this is about frustration physics. So the way you define frustration is basically if there are in a system, if there are competing forces or competing interactions, right? And these interactions which are not possible to be satisfied simultaneously, then we call the system is frustrated. I'll give you an example in the next slide. And all we know that these frustrations are real in physical systems, and very often actually because of these frustrations one finds very interesting and exotic properties of materials. Some of these materials are magnets. We'll be discussing about that. Some materials are typical solids where you see that the frustrations in the thermal expansion. Also, there are soft materials where you can see or you can study those frustrations. So let us talk about magnetism because this is a lecture on magnetism. So typically what you where you see frustration is this is a kind of prototype. So if you have a two-dimensional triangular lattice, right, and if you have an antiferromagnetic interaction between the magnetic moments which are sitting, as you see, which are sitting at the vertices at the corners, right? So then you see that if you let me take the laser pointer. Yeah. So you see, if it is a antiferromagnetic interaction in this triangular lattice, then you can have one up spin, one down spin here, right? So this is the antiferromagnetic, which is satisfying the interaction. This spin and this spin, this is also satisfying. But then if it is a triangular lattice, this and this in no way can satisfy this in triangular, no way can satisfy this antiferromagnetic interaction. So when it comes to this kind of bond or these two interactions, right, the spin, at least one of the spin doesn't know what to do, right? And that's what we are calling it a frustration, magnetic frustration in this case, which is coming into play because of the geometry of the system. So we call it geometric frustration in magnetism in this typical 2D triangular lattice. So please remember that we are talking about antiferromagnetic interaction and if it is a triangular lattice. But you can imagine now if instead of a triangular lattice, if you have a square lattice, for example, right? So then actually all these interactions would be satisfied. So we'll not see this frustration in this case. So therefore, as I said, there is a frustration of at least one spin in this case. There is one window which is disturbing a little bit. Okay. Right, I could minimize this. Okay. So now as a result of this frustration, this one spin that kind of fluctuates, or if you like, if you cool down the system, the entire system would order very differently than you know about the ordering of magnetism, like ferromagnetic or antiferromagnetic ordering, right? So the ordering is very different if it orders at all. The spins continue to fluctuate depending on the system. Spins may freeze at very low temperature. I'll come to that later again, but also the spins may avoid any kind of ordering, any kind of freezing till the lowest temperature, let's say T equal to 0 Kelvin. And therefore, at very low temperature or at the ground state, you have a large number of degenerate ground states, and therefore the entropy the ground state energy is given by, if you calculate it, it is given by 0.32 times Boltzmann constant times n, which is the number of spins. So you see, this is extremely large. If the number of spins in a system that you are looking at is large, then this energy to the system will have very large and high energy at the ground state, right? And it leads to very high entropy. So this is very interesting. And can't move the, okay. Right. Sorry, I had some issues with moving the slide. So now these fluctuating spins, if you look at, one can actually uh, talk about some kind of liquid here. So we all know this in ordinary liquid, right? We know all know the solids, right, where the atoms are sitting at particular locations, right? But in a liquid, the molecules, they form very dense and highly correlated state, but there is no static order like in a solid, right? So in this kind of magnetic systems, these fluctuating spins, right? So they are highly correlated, because one spin, as you have seen in this triangular lattice, that the spins know that the other spins, this down spin know that the other one is up spin, right? And because of this is frustrated, because it doesn't know if it wants to be a up spin or a down spin, because with one spin it satisfies one side of this antiferromagnetic interaction, but the other one is disturbed, right? So therefore this is highly correlated, but there is no order. And therefore often you talk about also cooperative paramagnets in this case, because there is no ordering in this case. So basically what you see is that this is very interesting, because you see there is a magnetic moment, localized magnetic moment at each lattice site of the triangular lattice, but then the system doesn't, system avoids any long range order. So that's what we call as a frustration, and which is actually coming from the fluctuation. And this fluctuation is defined usually by a fluctuation parameter. F, if this F is very large, very high, so we say that this is the system remains liquid till absolute zero temperature. What does it mean? So it means that temperature dependence can have two different kind of definitions for fluctuations. So one is the classical fluctuations, which is because of the thermal fluctuation of the spins. Typically, if you have systems with very large spins, so spins we quantify as the spin angular momentum, right? Integer multiple of half integer multiple of h cross, right? So you can define the spin angular momentum like this. If the spin is very large, let's say for example rare earth, for example, I'll come to this again in a few minutes. If the spins are large, then these fluctuations are observed at a higher temperature. But as the system is cooled down, typically, let's say at very low temperature, you see that those spins get ultimately frozen, and you have some kind of frozen spins at low temperature. So this is called, in those kind of systems can be classified as classical spin liquid. The system behaves as a liquid at higher temperature, and the system is because of the thermal fluctuations, right? And typically for large spins. On the other hand, if the spins are small compared to half h cross, right? In that case, you see that the fluctuations continue till the lowest temperature, absolute zero temperature. So in those cases, so these spins, these are actually phase coherent. They can be phase coherent. And if the fluctuations are very strong, then those kind of fluctuations with small spins and at t equal to 0 Kelvin, so these are called quantum spin liquids, because the fluctuations at the zero energy is because of the 0 point fluctuations. So typically these kind of fluctuations in quantum spin liquids, these are superposition states. So that means those spins, they can orient in different directions simultaneously. So this is what is this is a very interesting concept of quantum spin liquid, and this has a very practical implications. As you know, I'll not go into too much into details, but I'm sure I believe that on the first day of this lecture series there was discussions of about the quantum computing. So I'll show you that these kind of fluctuations can be understood from some entanglement between the spins, and these entanglements are important for the quantum computing, and for that point of view these quantum spin liquids are interesting. Okay, I'll come to this little later. So now let me diverge a little bit from this quantum spin liquid. I'll come back to this again, but let me tell you other kind of frustration, or other kind of systems where you see frustration. So it turns out that in materials called pyrochlores, systems, these are some oxides, right? Dysprosium titanate, holonium titanate, holonium titanate, etc. Right. So you see that these red ions, these dysprosium, holonium, etc. These are very large spin. So these are actually magnetic ions in pyrochlore lattice. So pyrochlore is actually, the lattice is kind of, these are tetrahedra and they share their corners. So these are called corner sharing tetrahedra. This is typically the pyrochlore lattice. And at each of these vertices, these rare earth ions, so these are actually the source of the magnetism. They sit at each of these vertices here. So they sit at the corner sharing tetrahedra, and if you calculate, using the Hund's rule, so these are very large spins. So typically, let's say for dysprosium, this is 15 and a half, and for holmium, this is 8, right? Also, this kind of systems, because of the crystal field effect, the spins, they orient along one direction. So typically these, because these are large spins, therefore the dipolar interaction is pretty strong, and you see very interesting effects because of these dipolar interactions. But also theoretically, one can understand the behavior from just the nearest neighbor. We call it an effective exchange. It's not the direct exchange interaction; it's an effective exchange interaction, which actually gives you the results that you would get from considering the dipolar interaction. So again, so in this system, it turns out that in the ground state, if you look at carefully the spins in each tetrahedra, you will see that each spin orients in a way that two spins in the system, they point inward towards the center of this tetrahedra, and two spins point outward. And that comes because of the frustration in the system, and that's how the system minimizes energy by pointing two in and two out. We call it two in two out kind of spins, and that leads to, because there are four different spins here in each of these tetrahedra. As you see this, there are four spins, and because of that, there are different ways of orienting those spins, and that leads to degenerate minimum energy state. And as I discussed earlier, because of this degenerate minimum energy state, there is also again a large ground state entropy. Now, these systems can be compared to water ice. So if you remember your school days, right? If you look at the water ice, H2O, you see that typically the structure is like this. That in this ice structure, two protons, they are closer to this oxygen and two are away from this. So these are the two orange color, these are the protons, hydrogen atoms, and so these are closer to this oxygen and two are out, two are away from from this oxygen which is sitting at the tetrahedra in this case. So we call it actually two in two out rule, and that's what we mean. So this is here it means two in two out. It means that two near and too far protons in this water ice, and because in this spin in this system, in this magnetic system, in this pyrochlore, let's say dysprosium titanate or chromium titanate, etc., the spins orient in a similar way. This is the orientation, by the way, of the spins. Two in, you see that this is one within this. This is again towards this center, and these are two out. So again, two in, two out, and that's why it is called spin ice, right? In analogy to the water ice, so this is called spin ice. So now, so this shows very interesting effects, and one has looked at. So as I said, that you can look at with using an effective kind of exchange interaction, and the interaction gives you a ferromagnetic interaction, and which is frustrated in this case. So the spins in this case remains paramagnetic. As you see, there is no proper long range ordering. But there is a strong correlation between the spins, because they always orient two in as two in, two out kind of orientation, and therefore this spin ice can be also classified as classical spin liquid state. So that's what I have defined earlier. And in this case, you can see in a pyrochlore lattice, the interesting thing is, because of these fluctuating spins, they interact with each other over large distance through kind of this. You can see that you can this kind of flux loops. If you see this, right? So this is a loop forming here, and around each of these tetrahedra. So this is one interesting properties one can look at how they behave. And the other important point is that important aspect is that in this kind of system, if you look at these individual spins as magnetic charges, so in that case, two in, two out state gives you a zero charge. Okay, magnetic charge is zero. So the way you think about it is that if the arrow is along this direction, you can consider that this is a positive magnetic charge, because flux comes out and goes in. So in analogy to an electronic charge, you can consider this as magnetic charge, positive and negative. And if you calculate the net charge in this kind of orientation, two in, two out kind of orientation, you see that the net charge at each of the vertices is zero. However, if one of the spins flips, right, in that case this is not zero anymore, this is an excited state, and in that case this will be either 3 times this q, this one of these charges here. So if this happens because of the system, since it wants to remain in the magnetically charged neutral state, so therefore and so another minus 3q kind of charge will develop somewhere else. Here in this case, this is green and red. So the difference in the magnetic state you see is here. Earlier, as I mentioned, this is two in, two out, the ground state. Now the excited state, you see that this is here, the one has flipped. So that means now three out, either it is three out, 1, 2, and 3. These are three out and one in. And in this case, this is three in, one in, another in, three in, and one out. Right, rest are all two in, two out, so charge zero. So therefore, so this is three in, one out. If you calculate, this is of opposite charge than this one, and that's why we call it a monopole anti-monopole pair. Monopole because this is a magnetic charge here, which if you have a charge here, in analogy to this electric charge, there will be a diverging field. So it's a kind of emergent magnetic monopole. So this is a classical excitations. These monopoles are not really a quasi-particle, right? So these are classical excitations. And when this was this kind of excited states were observed in experiments. I'm not going to talk about this in details. But as I said, this freezing of these spins are possible below at certain temperature, and that's why we call it also one can call it also as classical spin liquid spin liquid state. Interestingly, these are large spins, and therefore they can be also behavior of these spins can be also studied by simulating some kind of structures. where the spins are aligned along one particular direction. So what you see here, this is a network of different spins, meaning that these are some shape anisotropic materials. So these are elongated nanomagnets. If you can pattern them, these nanomagnets, then you can actually define the orientation of the magnetization along the long axis because of the shape anisotropy of these. And it turned out that this group from Princeton, they have actually fabricated those kind of structure, and they looked at the behavior of this, and it looks like that you can study those behavior of frustration in the spin ice in these kind of systems. So if you look at carefully, this is a schematic diagram, but if you look at carefully, you see that these are all in the vertex. You see that these are 2 in, 2 out kind of structure is at each of these vertices. But then one can have these many different types of vertices. So we call it, and we define these are as type 1, type 2, type 3, and type 4. Type 1 is 2 in, 2 out. You see, 2 in, 2 out. So this is less frustrated in this case. This type 2 is also 2 in, 2 out, but slightly different if you can follow this, right? So they're slightly different, but this leads to some frustration here. Okay, so energetically, these are this type 2 has, although it is 2 in, 2 out, but this is of higher energy than this one. Type 3 is just what I talked about, that these are charged states. So you see, this is either 3 in, this is 3 in, 1 out, and here 3 out and 1 in, right? So these are all the possible states. So this is of again of higher energy than this type 3. And in type 4, all 4 are out or all 4 in. So this is again the highest energy. So energetically, you can look at, and actually you can study their behavior. So this group have looked at, so these are real samples. This is an atomic force microscopy image of these patterned permalloy nanostructures. So these are all individual magnets, disconnected magnets. And then they looked at the magnetic behavior by performing magnetic force microscopy images. So magnetic force microscopy, you measure actually the gradient in the stray field of the vertical component of the stray field. So you see that each of the nanomagnets shows black and white patches. So that means these are kind of single domain. So if you consider these are kind of magnetic charges, white, let's say if it is arrow is along the white direction, so the black is along the this is the tail of this arrow, right? So accordingly, you can kind of find out the number of this percentage of type 1, type 2, type 3, etc. So these are kind of these kind of vertices they have studied as a different as a different lattice spacing. So one interesting thing is that in the real spin ice, natural spin ice, these effects one cannot study because these are at a low temperature, and also you can't actually control those spins. But here you can define those spins, and by design you can orient the spins along certain directions. You can look at as a function of the lattice spacing relatively easily. Of course, there is a lot of fabrication involved in this, not so straightforward, but you can do a lot of interesting physics in this. Okay, so these are called artificial spin ice because they mimic the similar 2 in, 2 out kind of behavior that I just discussed. So that what I showed here is a square lattice, but you can also make different kind of lattice. So here is another group. They have shown this is called hexagonal lattice, honeycomb kind of lattice, and one can study their behavior. So I'm not going too much into details. This is just to give you some idea. Again, here you can get some kind of charge state. Here, if I zoom in, you can see that so these are kind of different 3qm, minus 3qm kind of charges, monopole, anti-monopole, emergent monopole, anti-monopole kind of behavior, and you can study their dynamics in presence of field, etc. Those things. All right, so this was actually one example of another example of frustration and leading to some kind of classical spin liquid. In our group, we have been working on this. This is just one old studies where we have fabricated those single vertex, and we looked at the spins and their orientation in different magnetic fields. And you see at certain field, we actually see that this is this is a charge state, so we try to control them how to, in a controlled way, if we can if we can fabricate systems so that we can start one can study those kind of emergent monopole states. So this is an charge state where it is 3 out and 1 in kind of structure, whereas these are all 2 in 2 out, these are chargeless state. All right, so so in our group there is some focus on this kind of physics of artificial spin ice. So let me come back to the quantum spin liquid. Now, as you remember that I was talking about the low spin case for quantum spin liquid, high spin case for the spin ice, or the classical spin liquid case, which I gave an example right just now. So now look at what are the models, in what way one can fabricate or one can understand those kind of quantum spin liquid, or in a real physical system they can exist. So this is a model where it's called valence bond model. So this is a triangular lattice. Again, we are taking a triangular lattice, and then each of these islands, so each of these elliptical shapes, you see that these are at one side of these triangles. And so if you zoom in, so this is the zoomed in version, so you see that that these consists of two spins, right, antiferromagnetically aligned spins, and these are entangled in a certain way. So that means one spin here and spin here, or spin here and here, in a certain pattern, they are entangled, and they lead to, because these are antiferromagnetically coupled, so these are therefore this is spin 0, these are kind of singlet states. So this can be localized, and these are static. So although the ground state has spin 0, s equal to 0 state, spin singlet state, however, this is a concept, but this doesn't lead to a quantum spin liquid, because the system is static at absolute 0 temperature. The other issue is that it breaks lattice symmetry, right? Because you see a certain pattern in this, right? So, and the entanglement that we see are between the nearest neighbors, right? So there is no long range entanglement. So this model, so this is called valence bond model. So this bond, this is called valence bond, and I think this was introduced by Phil Anderson. Um, so this doesn't give a spin liquid state. Now let us go to the next stage. Now you consider the same lattice, right? But now you see that by design, if you consider these again, this entangled state, but they are not, they kind of break now the lattice symmetry, right? So symmetry is broken. Sorry, the symmetry was broken in the other case, so this is now symmetry, and so you can kind of add up the other states as well, so where you can consider any kind of nearest neighbors, right, unlike the other case. So I hope that you can appreciate this. So this is kind of lattice symmetry is broken, and here there is no preference for any specific pair of entanglement. That's what I mean, right? So in the first case there was a preference for pair of entanglement. There is no preference here in this case. So in this case, this is called the bonds, of course, they fluctuate, and these are called valence bond liquid. And so if you look at the wave function of the entire system, so this wave function will be superposition of many different pairs of entanglement, right, as you see it here. So these wave functions are called resonating valence bond. These states are called resonating valence bond state, and they lead to quantum spin liquid. The other example could be this. One can consider, in addition to what you have just seen, there can be also long range entanglement like this. Like, so this, you see that this banana shaped one, so that means actually the entanglement between spin here and spin here, these are antiferromagnetically aligned. So therefore, there is no specific pattern of entanglement, and there is a long range interaction. So this leads to the fluctuation, and those fluctuations stay till absolute zero temperature and give you this quantum spin liquid. So this is one way of understanding those theoretical concept of quantum spin liquid, which is resonance valence bond model. The other model was given by Kitab. I think because of the time, I will skip this. But it's a different Hamiltonian, and if the spins, if you see that this is a hexagonal honeycomb lattice in this case, these K's are called Kitab interaction. So if the spins are all you have all these components. So it shows that I'm not discussing too much into details. It shows that within these models, also with these kind of interactions, the ground state could be quantum spin liquid state. All right, so what are the features? So if you look at quantum spin liquid, so in a quantum spin liquid, there has to be an absence of long range magnetic order. There is no ordering. So that means there is no order parameter that you can associate with this quantum spin liquid. There is no spontaneous symmetry breaking of the crystal lattice or spins, as I have just discussed. Long range entanglement between the spins one should have, and as a consequence, this is fractional spin excitations. Yeah, I think I'll possibly skip this discussion about the spin excitations in this case for the want of time. So typical materials, as you see, these are triangular lattices, Kagome lattice, something like this, right? And also the pyrochlores, there may be some quantum spin liquid with if the spins are very small. In the artificial spin ice, what I've shown, these spins are pretty large, and that's why those are classical spin liquid state. And why these are interesting, I think I have covered that. So they don't have any local order parameter, so it's interesting to study their behavior. And long range entanglement, which is essential ingredient for quantum communication. All right, so I'll skip this excitation, as I said, and now let me go to the next topic that I wanted to, next kind of materials. So far I've covered the frustration, quantum spin liquid, and artificial spin ice to some extent. Let me talk a little bit about the magnetic skyrmions. Um, I just like to play this video. Is the video visible to all of you? Is the video visible?
Yes, sir. Video is played.
Video is playing. Okay, very good. So what you see in this video. Let me try to play it again. So what you see in this video is that this is a water in a channel, right? So it was discovered by I think Russell. Um, I forgot the year. That if you take a boat in a canal or in a channel, and if the boat stops suddenly, then there is some kind of solitary wave forms, and the solitary wave can travel to very large distance. So the year is here, in 1834, Scott Russell. So let me read out this. The mass of water in the channel, which the boat had put in motion, rolled forward with great velocity, assuming the form of a large solitary elevation, a rounded, smooth, and well-defined heap of water, which continued its course along the channel, apparently without change of form or diminution of speed. So what you see again, let me put it here. So this is in the laboratory. I've taken it from YouTube. So you see that if such kind of waves are formed, and you see that the wave travels with a large velocity without so this is a solitary wave in water without being destroyed, right? So these are called solitary waves, and the particle part is called the solitons. So the name solitons was coined by Martin Kruskal of Princeton University and Jabuski from Bell Labs. So the interesting effect in this case, what you see is that these kind of solitary waves or the solitons, they preserve their shape not only while in motion, but also during interactions with other solitary waves. So in other words, they behave as a particle, solid particle, and these particles are called solitons. So in physics, can't move. Sorry, my slide doesn't move. Okay. So yeah, so in physics, in different kind of systems, these solitary waves are interesting. So let me quickly go to our come to our topic. So the question is, can these solitons be formed as a very stable entity in two-dimensional or three-dimensional real physical system? So for magnetism, so let us look at the magnetism. So what we see here is that we need this concept of chirality. So it distinguishes an object from its mirror image, right? So typically our hands, let's say, if you put your left hand and right hand, these if you put them together, they are not the same, right? So they can't be superimposed, and therefore we call it a chiral entity. Whereas if you have this flask, right, if you take the mirror image, they can be superimposed, and therefore these are called achiral systems. Now it turns out that in nature there are crystals. So if you have a chiral crystal, so that means if you do not have a mirror symmetry, right, mirror symmetry in this case, a typical example is iron germanium. We call it also non-centrosymmetric. Right, so in this case, iron atoms are in orange color, right? So if you have that, then the spins of these iron atoms or the iron ions shows some kind of chiral signature in their magnetic moments. So what you see here is the magnetic moment along. You see that this one particular direction. So that's what we call it a chiral, right? If in the right-handed case, if the system is like this, then the rotation of the magnetic field is anti-clockwise, and that's why. So that's what you see here is that the magnetic moment depends on the chirality of the system, and that is very interesting. So what you see here, that if there is a non-centrosymmetric crystal, so the spins, they, instead of if you remember your exchange interaction gives you up or down spin, right, collinear spin. But now, if because of this chirality or the non-centrosymmetric crystals, the spins will cant with respect to one another. So this leads to very interesting effect. So effect in systems. So in let's say in bulk systems, so this leads to some kind of solitons, right, as you have seen in the water waves. Now these are the solitons which are formed in these magnetic systems, in a ferromagnetic system, and because of this, these are topologically stable objects, right, which we call skyrmions. And where you see that the spins kind of orient, if you take a football, so the spins will be in such a way that all the entire surface of the football would be covered, right, with all the direction of the spins are spins will be there. If you take a projection of this three-dimensional figure into on this, then this system looks like this. This is the two-dimensional projection of this object, right? So now in this case, now it is easier to understand here. In this case, you see that the center of this, the spins orient opposite to the edges, those of the edges, and in between the spins cant along these directions. So in this kind of system, so this the major interaction which is responsible is called Giacomo-Moria interaction. So we write this is a Hamiltonian. The d12 is the vector. So if you have two spins given by the spin angular momenta S1 and S2, so this is how you write this Hamiltonian. So that means the net interaction, net Hamiltonian, is due to the exchange interaction, which is S1. This is the dot product, right? J S1 S2, which all of you would know. In additionally, there is this additional additional Hamiltonian because of the Jelossonsky-Moria interaction, this kind of interaction. So, so this they can be quantified as a topological charge or the winding number of this, and one can calculate this topological charge. I think some part of this was discussed in the last lecture, so I'm not going into too much into details. So this, from our basic definition, this we call it a block type skyrmion. Where the spins rotate in parallel to this to the surface, whereas these are called nil skyrmion, and these are observed in typical some thin films. I'll come to that little later. Okay, so as I said, Jelossonsky-Moria interaction is important. So you get it in some kind of natural systems, as I have shown, iron germanium crystals, for example. There are some other crystals of that type where you see this. But in those cases, those kind of topological features, topological objects, which can be stabilized at low temperature. Now, because these systems are topologically protected, so that means you can't easily destroy those objects. So one can think about using those for some applications, let's say in magnetic memory. But then you need at room temperature, those objects at room temperature. So people looked at this, how to stabilize those features at room temperature. So there, the idea is that if you have a ferromagnet and a heavy metal interface, right? So because of these heavy metal, you have a strong spin orbit coupling, which leads to this Jelossonsky-Moria interaction in a way that it stabilizes those kind of features, these solitons at room temperature. Okay, so now typically they would look like this, right? So these are different handedness, and you see that the skyrmions are of different skyrmions. These are isolated skyrmions, and they can form also skyrmion lattice under certain conditions. So these skyrmions, as I said, there's an anti-parallel magnetization at the skyrmion center, right? So if you apply a field in the skyrmionic phase, if you apply a field, let's say along up direction, so if all your other spins are along opposite direction to the center, right? And therefore, if you increase the field, this becomes energetically unfavorable in the magnetic field, and therefore the core diameter slowly shrinks as a function of the field. So this is the core diameter. If you plot it, it becomes like this. So this LS is the core diameter, which is a function of field, which decreases. Okay, so just one or two images for this. So these are real space observation of those magnetic skyrmions. These were taken by Lorentz transmission electron microscopy images of this. This was the Tokura group. So there was a lot of speculation at the beginning that those kind of systems are really stabilized. But this group has for the first time shown by real imaging that this kind of chiral systems, chiral textures, magnetic textures are stabilized in certain systems. So one can do so they have looked at as a function of field. You see that they have stayed at 25 Kelvin, and as a function of field starting from zero field. At zero field, this is kind of elongated structure, and then slowly as they increase the field, there are some of these round objects start appearing, and they have later found out that these are kind of magnetic skyrmions, right? So they have looked at also from the simulation, and then they have properly identified those phases. So there are also some mixed phases, right? So let's say ferromagnet and skyrmions. This is fully skyrmions phase, and then once they do it, once they've done it, then they have drawn this phase diagram, field versus temperature phase diagram. Try to locate at exactly which range of the field and the temperature those skyrmions phase exist. So this is how the phase diagram looks like. All right, so I think I am Manoj. How does it look like? So I think I'm at the end of this first lecture, right? So I guess I would skip this van der Waals magnets.
Yes, sir. This was really interesting to see nice pictures, images, new magnetic orders. Yeah, so it is up to you, sir. If we can cover, then we can go to this topic. Otherwise,
So
maybe
maybe just
briefly
five
we
minutes
can
I'll
talk.
take. Is it all right? I just take 5 minutes just to talk about the van der Waals magnets, maybe 2-3 slides or something. Is it all right?
Yes, sir. Yes, sir. That will be really nice.
Okay, sure. Yeah, so now different kind of magnets. All of you know that the graphene made a lot of impact, and after graphene, people are looking at magnetism in graphene, because if you can make if you have magnets in thin film, so that could be very interesting for the spintronics, future development of spintronics and other kind of spin based devices, right? Let me directly come to this. I would assume that many of you are now familiar that there are magnetism observed in the two-dimensional crystals. Um, so I think it's important just to point out that the initially the Marmin-Wagner theorem, which ruled out the long-range ordering in the two-dimensional case because of the fluctuations that we have discussed, spin fluctuations. But it turned out that if you have and uniaxial anisotropy in a system, the long range order would persist. So the first frustration cannot destroy the long range ordering in this case. So all the magnets that you have, two-dimensional magnets, those have some uniaxial anisotropy. So I'm just talking about one particular crystal here, system, which is iron 3 germanium telluride system. This is the space group of these, and just to show you that so this group in 2000, I think 2020, so they have first reported that that iron germanium telluride system shows signature of ferromagnetism. The issue here is that if you, it is very thin film, yeah, so maybe this one. Right, so there is a way to fabricate those. I think I will not discuss this technical aspect, but let me point or refer to this, that this group was able to successfully study the layer dependent behavior. So if you look at layer dependence, so starting from monolayer to going up to bulk in a very systematic way, and you see that there is the resistivity behavior of the system also changes drastically. So it starts from metallic like behavior at a temperature to almost semiconducting like behavior when you go down towards towards monolayer. But further interesting thing is the magnetism, right? So the bulk looks like this. This is the hysteresis loop, which was measured by anomalous Hall effect, right? So if you go down to 6-layer, 4-layer, and the coercivity is changing, but they see that the hysteresis persists up to 1 monolayer. Okay, and so if you look at these rxy, which is the anomalous Hall effect, as a function of temperature, from these measurements, and if you follow that, then you see that this is this magnetism, this anomalous Hall effect is because of the magnetism. I think I'll discuss in the next lecture a little bit later. But if you consider that this is the magnetism, then you see that the magnetism as a function of layer, layer thickness, this goes down, the transition temperature goes down as a function of number of layer. So okay, so yeah, so there are different groups who have reported these ferromagnetic hysteresis loops. I think I'll discuss a little bit in the next lecture about that aspect. Also, the skyrmions that I have discussed, so people have actually fabricated devices now, because since you have a two-dimensional magnet, it is possible that you can fabricate devices with magnets and some other strong spin orbit coupled material. So in this case, this is tungsten ditelluride, and where you have a strong spin orbit coupling. And if you remember, I just showed you in using a schematic slide that if you have a ferromagnet and then heavy metal with a strong spin orbit coupling, that leads to a Jalossonsky-Moria interaction, which cants the magnetic moments, the spins, and that leads to magnetic skyrmions in some systems. So this is one of those one such work in these van der Waals magnets. People have reported magnetic skyrmions. So these are magnetic skyrmions in these van der Waals magnets. So so this gives a lot of opportunity to to tune the material parameters, material interactions, The interesting thing is all the magnetic multi-layer heterostructures typically one grows the heterostructure by sputtering method, which is not really very clean. The interface is not very sharp. But if if two-dimensional materials, which are really very nice crystals, so if you can grow two-dimensional materials, the interface quality could be excellent, and you can study those behavior in a very very clean systems. So I think with this, I would like to stop here and take a small break before we start the next session, unless there is any question at this stage.
Okay, sir, sure.
Yeah, I think someone has asked if there is any signature of skyrmions in transport. Yes, there is. I will discuss about that in the next lecture. So if there is no question, then can I unshare?
Yes, sir, please. We can reshare and restart the things after 5 minutes, maybe 5, 7 minutes.
Yeah. Okay. So maybe at 4:10 or something. Someone has asked about the two in two out. Maybe I will address this in the next lecture then.
Okay, sir. Okay. Fine.
Thank you. So is the slide visible?
Yes, sir.
Okay. All right. So can I start, Manoj?
Yes, yes, sir. Please.
Okay.
And I think we will address all the questions towards the end of this lecture.
Okay. Fine.
Yeah, so maybe I would ask the participants to keep posting the queries in the chat box, and those will be addressed towards the end of the lecture.
All right. Okay.
Okay. Thank you, sir.
Yeah, sure. So I'll try to finish maybe at least 5 minutes before 5 or something. All right. So here, so far we have discussed about a few different kind of quantum magnetic materials. So I'd like to give little bit of idea about how to measure, how do you see the signatures, and particularly I will try to focus on the magnetic skyrmions and the electrical transport measurements, because some of the results we have already seen now. But let me give you. Let me start with the quantum spin liquid. So, so as you understand, as we discussed that quantum spin liquid by definition it means that we want to look at the fluctuations spin liquid behavior at the zero temperature, 0 Kelvin, and ideally it would require the measurements to be done at absolute zero temperature, which is of course not possible, right? Because there is which is not possible, and because there is no long range order, there is no spontaneous breaking of lattice symmetry, which you understand now. uh, there is also no local order parameter, so this is extremely challenging to directly define a particular signature in a system. So therefore a couple of different kind of measurements are carried out. Usually idea is to prove that there is no magnetic order, there is no spin freezing. As I said, if it is for classical spin liquid system, the spin, although there is a thermal fluctuations at higher temperature, but at very low temperature, the spin freezes. So, but that's not a quantum spin liquid. So you have to, one is to prove that there is no spin freezing down to the lowest achievable temperature. So now in low temperature laboratory, routinely one can go using dilution refrigeration, one can go down to even 10 millikelvin temperature. So whatever the lowest achievable temperature, one needs to go and see that there is no spin freezing happens in this case. So if you see that there is no spin freezing, then possibly you can kind of say that maybe this could be a candidate for quantum spin liquid. And typically one looks at the low spin systems, right, as I have mentioned earlier, which are where the interactions are predominantly antiferromagnetic interactions, because that's how we have defined our model, resonating valence bond model. And uh, all right. So for example, one can measure the magnetic susceptibility. One can measure, I mean, typical measurements for magnetism, right? One can do inelastic neutron scattering measurements. Other than that, thermal conductivity, thermal Hall conductivity, nuclear magnetic resonance, electron spin resonance, specific heat, etc. So those carry specific signature. And together, from multiple different measurements, one can possibly identify that okay, there is possibly this is possibly a candidate of quantum spin liquid. So I'm not going to discuss actually all the measurement details, because many of these measurements are straightforward, but I try to skip this. Rather, I thought that I will possibly go for magnetic skyrmions and then discuss a few things here. There are certain questions also on this. So so this was about the quantum spin liquid, and it's very rare to find. Actually, people are still searching in different kind of materials, and typically, as I said, these are low spin systems. If you want to look at quantum spin liquid, you look at the low spin systems. You look at the antiferromagnetic spins, and ideally in kind of two-dimensional systems. But there are also report, these are very few, very rare, but there are also report of quantum spin liquid in three-dimensional systems. So let me start with magnetic skyrmions. Right. So one thing that what I've shown you in the last, while discussing the quantum materials, is an image of those colored images of vortex-like features, and which I said that these are magnetic skyrmions. So this is, I have not mentioned what this measurement is. So this is called Lorentz transmission electron microscopy. So Lorentz TEM, all of you would, or sorry, transmission electron microscopy. Most of you would know, I believe, how it works, right? So you have a source of electrons. What you do here, the electrons, they when they travel through these, so these are the electrons or electron waves, let's say. So these are the magnetic materials with different kind of domains, right? So pointing magnetization pointing outward, pointing inward. So this is a domain wall here, domain wall here. So these are magnetic domain walls. And now, because these are electrons, so this is in the transmission mode, transmission electron microscopy. We call it Lorentz transmission electron microscopy because based on this, the basic ingredient is this, that these are electrons. When they move through this magnetization, different magnetization in the specimen, they are affected due to the Lorentz force, and they change their trajectory, right? So Lorentz force, which is velocity cross the magnetic field, which is coming due to the magnetization in the sample here, and that leads to the different trajectory of this. And then if you can if you focus it on the screen, you can kind of get this kind of behavior at the domain wall, because you see there are sorry so there are large intensity at this point, small intensity at this point, so that you can identify that these are domain walls. This is in brief, rest everything. I mean, there are, of course, many other things to be discussed, but this will be possibly more with the, those who are really trying to do this. But if you remember this, then we can go to the sample. So what you see is that in with this simple, this principle, this we call it a Fresnel mode, but there is also a focal mode. I'll not discuss it here. Uh, you see that if there are domain walls like this, one can actually identify those domain walls. Uh, if you ignore all other cases, all other details, right? So now, so this is the image on the screen, right? So these are at, I believe, at different magnetic field or different temperature. I think there are slides on that. Um, this is the scale bar, 90 nanometer. You see, these are elongated structures. So this is roughly, let's say, 200 nanometer by 200 nanometer, possibly. And within these are kind of all the colors that you see. They actually tell us about the magnetization orientation of the magnetization. Okay, so these are kind of two colors, so the orientation is like this. But here, in this case, figure B, you see that, so this is a different field. So if we apply, so this is a skyrmion sample. Now, in this case, sorry, let me put the pointer, laser pointer. So this is the sample now, right? So if you have a elongated magnet, magnetic lines of flux, then you get this kind of behavior. Then when the skyrmion is stabilized in certain field, right? So you see that these are the kind of different color coded uh, features here. So they tell us about the different orientation of the spins at different positions. So if you kind of analyze this data, so this is what exactly it is, right? So this is the magnetic skyrmions that we have defined earlier in this. So here the spin, so this is the block skyrmion, because the spins orient along certain direction, right? So, and the field is out of plane, out of the sample, so therefore the outside, so the core, at the core is opposite to the field direction, right, as we have discussed earlier, and this is out of this field direction, right? So, and this leads to, in the Lorentz transmission microscope image, this leads to this kind of colored images. So this group they have also simulated this, and then they find exactly this, so they could clearly discuss that this is the magnetic skyrmions. So Lorentz transmission electron microscope is one way, to image this, image the magnetic skyrmions. Also, there's a magnetic force microscopy. If you look at the literature, there will be many literature now, many papers, reports where images will be, images will be shown, which were taken using magnetic force microscopy. Right, so this is one such image of, this is metallic multilayer. Sorry, I forgot to mention, this is Christos Panagopoulos in National University of Singapore group. So these are multi-layers, magnetic multi-layers, and if you remember that ferromagnet, heavy metal, that leads to the Gialesowski-Moria interaction at the interface, we call it interfacial Gialesowski-Moria interaction on both the sides, and that leads to this Gialesowski-Moria interaction is important, if you remember, for the canting of the spins, and that leads to these kind of structures, right? So these are kind of chiral textures, and if you apply magnetic, so at zero field there is no skyrmion. These are kind of elongated maze-like pattern. But if you apply field, let's say in 100 millitesla field, there are some round objects here, round objects here. This is the opposite field, 100 millitesla and minus 100 millitesla. That's why the color contrast is different here. The yellow has turned blue and blue has turned yellow. One thing you should remember is that these just show you the stray field. So with the magnetic force microscope, you measure the stray jet component of the perpendicular component of the stray field coming out of your sample. So you can't actually check the orientation of the magnetic moments within these round objects like you can do it in Lorentz transmission microscopy. So nevertheless, Lorentz transmission microscopy is not always available in with many research groups. So, but MFM performing measurements with magnetic force microscopy relatively easier. So now that that there is a good amount of knowledge about the systems and also the how the skyrmions should look like, people accept it as a magnetic skyrmions. But otherwise, this could be also some other texture. It may not be from the magnetic force microscopy images. It is not possible to straight away say that these are magnetic skyrmions. The reason is that you do not see the chirality of the spins. All right, so these are two typical imaging techniques that I thought that I would discuss. Now, typically, if these skyrmions are to be used for spintronic devices, right? So if you want to use them for spintronic devices, then you can't take your sample under a microscope and then see the skyrmions. You want to read this electrically, the signature of the magnetic skyrmions, right? So therefore, electrical transport behavior, understanding the electrical transport in magnetic skyrmions is important. Sometimes my slide doesn't want to change. Okay. So let us look at the signatures in the magnetotransport. Now, as you know, this is a ferromagnetic system, right? So typically, if you have a ferromagnetic system, if you perform a Hall effect measurement, right, so you measure anomalous Hall effect. In addition to the ordinary Hall effect, right? So ordinary Hall effect is proportional to the external magnetic field, which I am saying Hz, right? Perpendicular magnetic field. And then additionally, if it is a magnetic systems, you get the anomalous component, right? Which is proportional to the magnetization in the sample. This anomalous Hall effect is due to the broken time reversal symmetry, which leads to magnetization and also the spin orbit coupling. So so this anomalous Hall effect has both intrinsic and the extrinsic components. So extrinsic components are skew scattering plus side jumps. So those who are into this magnetotransport, they possibly have studied this. But the intrinsic component is that there is a Berry phase related component, which is because of the spin orbit coupling. So I'll try to discuss this, what is the Berry phase and how it is important. So this Berry phase is a geometric phase, whenever a system evolves adiabatically along a cyclic process. So let's say this is a cyclic process. If the system with a certain velocity evolves over time in a certain parameter space, then the wave function of this system, if it is an electron, the electronic wave function, will acquire an additional component, additional phase, right? So if you write it I theta n and stands for particular band, right? So there is a gamma times psi n t, Okay, so this is an additional phase in addition to theta, where theta is a dynamical phase. This is what this all of you know this. Okay? So this additional phase, so this dynamical phase comes from the band structure, right? So this dynamical phase, this additional phase gamma nt, this is called the Berry phase, and it is defined as this, which is because of the adiabatic, adiabatic process in this case, in this parameter space. So that means if a system evolves along a cyclic process in an adiabatic way, then there is an additional phase component which will be associated to the wave function of this system, and this phase is called Berry phase. Let me show you what it does. So in that case, then the velocity component in presence of the electric field, right? So if you apply electric field in a system, so this is the velocity that you know from your band structure, basic solid state physics, right? You know the E versus K band structure, and then this is the first derivative of this, so that you get gives you the velocity component. But if you have a Berry phase, then in that case there is an extra component, extra velocity component, which is given by this electric field which you apply, and this gamma is related to this Berry curvature that we have discussed. This Berry phase, and this is called the Berry curvature. Gamma is omega is called the Berry curvature of the nth band. So that means if the velocity component in this case will have an additional component, this one, right, which is perpendicular to the electric field. Okay, so this is the electric field which you apply, and this is the Berry curvature, right, which is because of the Berry phase that you got, that we have just defined here. So because of this additional velocity component perpendicular to the electric field, you have an additional Hall current. And this additional Hall current, we call it anomalous, we are calling it anomalous Hall effect, and this is the intrinsic anomalous Hall effect in this system. So this Berry curvature in K space, this is in K space, that leads to some intrinsic anomalous Hall effect that one can measure. Sorry, my slide is something happened here. Now let us talk about skyrmions. So once you have skyrmions, magnetic skyrmions, you see the spins. Hopefully you are now familiar with this kind of spins. Now you consider that one electron with a certain spin, it travels through these skyrmions, right? So what it finds is that on the way it finds it spins in a different direction, right? And if it moves adiabatically, then basically because of the exchange interaction, to minimize the energy, so its spins will be oriented according to these spins, underlying spins here. So this kind of ribbon kind of thing, this is the twisting, and this is the this is to show how the spin will change from one end of this fermions to the other. So this goes to a full circle, as you see in the color, right? So 360-degree rotation. So this goes adiabatically in a cyclic process, but not in a K space, but this is in a real space. So these electrons now this is in a slowly changing. This is the exchange field, right? Or we call an emergent field in the adiabatic limit. Then these electrons will acquire a Berry phase now in real space. Now in real space, this Berry phase, in analogy to the Berry phase in the K space, there is an additional Hall component. And because these features are topological features that we have discussed, right? This Hall component, because of these are called topological Hall effect. This additional Hall effect is called topological Hall effect. So that means if you have a system, magnetic system, and you measure the Hall effect, you will have ordinary Hall effect, which is proportional to the external field. You will have anomalous Hall effect, which will be because of the magnetization in the sample, and the intrinsic effect that we have discussed. In addition, there will be also this topological Hall effect because of this real space Berry phase. So that means the total Hall effect will be sum over all of these three. Now this topological Hall effect one can define. So theoretically one can show that this is this is given by the spin polarization of the system. Ordinary Hall coefficient, this is the density of the skyrmions, right? So if you are given system, you have certain density of the skyrmions, and this phi 0, this is the flux. So this nsk, nsk, this is the skyrmion density, and this flux of the skyrmions. So this gives you the total emergent magnetic field, which is BEF, right? So in this emergent field associated with this skyrmion density, this gives the additional Hall effect perpendicular to the electric field. So this topological Hall effect, we are calling it a real space Berry phase. This was first reported by this group in skyrmions, skyrmionic system, which are block type skyrmions, which were observed in manganese silicide. And you see that this system has a skyrmions, between in a very small temperature window between 28 to 29 Kelvin. Right, within 1 degree Kelvin, the skyrmions are stabilized and then it goes away. Now, this group has very carefully actually measured. You see that every 100 millikelvin they have measured this, and then they see that there is a very nice feature developing in the Hall effect, right, as a function of this function of temperature. Now, as you see, these numbers are very small. This is some few tenths of nano-ohm centimeter, and it's extremely tricky to measure such kind of signal from this. And what one does is one removes, when you do the measurement, you cannot measure the topological Hall effect separately, right? So you measure the total Hall effect, and then you subtract, you measure from the total Hall effect, you subtract the ordinary component, you subtract the anomalous component, and then what is left over is your topological Hall effect, and that's what they have plotted here. Yeah, so I'm highlighting this just to note that this is a very small temperature range, and also the Hall effect that you see is very small, nano-ohm centimeter. So several years later, when these room temperature skyrmions were discovered, right, in the multi-layer thin films, and these typically have nil skyrmions, as I have discussed in my first lecture, right? So this group from Singapore, they have actually measured this topological Hall effect in this kind of skyrmions, and they have also followed. So what you see here is the topological Hall effect as a function of magnetic field. And what they see is that they see a peak in one side of the field and the deep on the other side of the field, right? And so then they map this with magnetic force microscopy images of the magnetic skyrmions at different fields, right? And I think I do not have a proper slide here, but one can calculate the skyrmion density. You can see that the skyrmions are stabilized at certain fields, right? And one can determine actually the skyrmion density, and then one can relate it to this topological Hall effect, and they found a very good relationship between this. This is the not the same sample, but the same group, but different samples. Again, different measurements. They show again that the the topological Hall effect and skyrmionic system. So at least 3 different field values they have shown that this is 0 field, no skyrmion. These are kind of elongated texture. Positive field, there is a peak here. There are a certain number of skyrmions. Negative field here, there is a certain number of skyrmions in this case. All right, so I would just like to show we are working on those aspects. These data are not published, so I'll not discuss too many. But let me show you that these are kind of the multi-layer heterostructures that we are doing the measurements on. And oh, sorry, something has happened. So this has not come out properly. So this is the magnetization. This is the total Hall effect, and this is the topological Hall effect that I have just discussed, right? So here again, we see that very peak and a deep kind of structure. And additionally, we see another hump-like feature also in our case, very robust. And then we measure actually as a function of field, we measure the magnetic skyrmions coming from elongated structure to some field, very nicely and dense skyrmions that we see. So, from the transport, one can look at those topological features and topological Hall effect, and one can identify the skyrmions. But I should warn you that this effect is debated in the community right now, because there are many different systems which show some kind of extra Hall effect or topological Hall effect in the system, which doesn't necessarily indicate that there are skyrmions in the systems, because there are not real ingredients for skyrmions to stabilize, and there are many works which have just reported those kind of Hall effect features, but without showing any imaging of the magnetic skyrmions. So there is a lot of debate to understand. Actually, theoretically, it looks like pretty challenging, because there are many other different effects which can lead to this kind of features also. So at this stage, it is not straightforward to say that, okay, if you see those kind of topological Hall effect, it means that there are magnetic skyrmions in this. This is not the case at this stage, unfortunately. So let me then quickly discuss a little bit about the 2D magnetic materials, van der Waals magnets. So I'll take one particular example, what you learn from this. So one of the um, important aspect in this van der Waals magnets is, if you those who are working on magnetism, you know that you typically do a squid measurement or VSM measurement to measure the magnetization of these kind of materials. But all of these equipments come with some kind of sensitivity limit, right? So if you are really going towards the two-dimensional limit, so that means your sample volume is very small, and if your magnetization magnetic moment is not very large in the sample, you may not be able to measure anything with the squid or for the two-dimensional devices. So what one does is, typically one measures the anomalous Hall effect, and as I just mentioned, now this anomalous Hall effect can be considered to be proportional to the magnetization. So looking at the anomalous Hall effect data, one can kind of estimate, or one can infer some conclusions about what is happening in the magnetization in the system. So I'll show you a few examples of that. So one of the problems, so this is some of our work that we have been doing. So one of the problems that with this iron germanium telluride, the system which I have already shown that there are people have reported there are this is a ferromagnetic system. But there are 2 or 3 reports where people have found very intriguing behavior, like thermal hysteresis loop, and that people have considered that this is possibly because of some kind of competition between ferromagnet and antiferromagnetic state, ground state, in the system. But so far there was no direct um, uh, uh, result from to support or negate this kind of observation. So it turns out that these are real. These kind of thermal hysteresis loops are real, and then one needs to find out where does this ferromagnetism and antiferromagnetism come from in this case. So let me look at sorry. The other side, I'll skip this. Yeah. Um, so we were looking at this, that where does this come from, ferromagnetism, antiferromagnetism? If there are some suggestions that there could be interlayer antiferromagnetic coupling uh, between the layers, but that this was not settled. So there was no signature of any competing phases from electrical transport which was reported so far. So this is the kind of sample. So you always have to characterize the sample. So we do typically X-ray diffraction, we do Raman spectroscopy, etc., and then we try to determine the good quality of the sample. And then we have reproduced the thermal hysteresis loop that people have reported, because we wanted to see that this is the case, and then we wanted to dig out information from this. So in our group, we are actually measuring this. So this is not a research talk, but I will just mention few important points that we understand so far, and how do we kind of characterize this behavior. So these are kind of bottom electrodes, right? On top of those electrodes, we have fabricated the iron germanium telluride, and top of that we always encapsulate this with a inert element which is related, which is hexagonal boron nitride, HBN. So HBN is on the top, so that the surface of the iron germanium telluride after fabrication is not oxidized, because the oxidation may lead to changes in the magnetic behavior or any kind of properties of the system. So these devices are fabricated all in the glove box in a very clean environment, and then encapsulated within the glove box itself. All right, so this is kind of the parameters of the glove box, and then we do the measurements of resistivity just to see, not that that is the only one we have measuring, but this is already reported. We just kind of ensure that the system is good. Right, so this is our data. My student Nisha, who has submitted this under review right now, the work is under review, and this is in the literature, so it matches pretty well. And then what we see is that we did very carefully. Actually, what we see is that when we measure the anomalous Hall effect as a function of field, right? So we see that there are two switchings, very sharp switching. Nobody has reported so far this kind of switching. People have reported single switching in this case. That means just one sharp jump, another sharp jump that we understand. But so we'll try to look at this in detail. So we did some temperature dependent measurements. So it shows a very systematic behavior in the temperature dependence of this. And you see the switching goes away. Well, we call it a switching, by the way. So this is the magnetization reversal. It switches twice and then goes to the next stage, right? Or the other magnetization changes to the other direction. So this is a temperature dependent behavior. So we try to understand this, what is going on in the system, why we are getting the switching from. Now, so this is obviously clear that there are two levels of magnetization reversal, right? Reversal, and that may happen. So if you consider that, okay, so maybe there are different magnetic phases which switches differently at different coercive field. But this is not the case in this case, because from X-ray diffraction and Raman spectroscopy results, we know that there are no other phases in this. So uh, typical magnetization reversal that you study in bulk systems, these are for domain wall motion based magnetization reversal, right? So domain wall nucleates and then it propagates through the sample as a function of field, and that leads to the hysteresis loop, right? So the hysteresis loop is not like sharp here. Hysteresis loops are typically, if you remember, the kind of S kind of behavior that you see, right? Whereas here, just at one particular field, the system switches, and after some time, certain field, the system switches again. And it is not at all random. It is all very systematic, as you see from the temperature dependent measurement. So that must be intrinsic. So that means there is no other extra phase. It cannot be also domain wall based, because this is very sharp switching, which we do not expect. So we started looking at, we did some theoretical calculations with a colleague of us, did some DFT based calculations, and it shows that so there are different kind of magnetic configurations, and we considered and we tried to look at which are the energetically favorable. So it looks like that uh, so there are this is all ferromagnetic. So there are different kind of two different iron ions in each layer. So one is Fe2 plus and another is Fe3 plus, I think, which is mentioned here. The blue is Fe3 plus and the magenta is Fe2 plus, right? So two different kind of iron atoms. Now if you consider this as ferromagnetic state, you consider that a different kind of antiferromagnetic state, and yeah, so there are three different kind of antiferromagnetic state possible in this case, and then we calculated all of their energies, ground state energies, in this case, this, all of this. Okay, and we see that the lowest energy state is this one is the lowest energy state, which is, we call it you know uh, energy of an AFM3 state, which is sorry, minus 26.9514 electron volt. Okay, now once we know that this is the lowest energy state, now here what we see here is that that uh, two iron atoms, Fe3 plus and Fe2 plus, they are ferromagnetically coupled. right? Fe3 plus Fe2 plus is ferromagnetically coupled, and Fe3 plus Fe3 plus, they are antiferromagnetic coupled in each layer. So that's what is very interesting, and we find that we have calculated the exchange interaction between these two, and we find that this exchange integral parameter J1 equal to 0.47, and J2 is plus 1.29. So one is the ferromagnetic and another is the antiferromagnetic interaction in this case. So based on that, we figure out that the ratio between this J2 and J1 is 2.64. And interestingly, we find that from the experiment, this change, let me go back to this change delta, let's say if this is delta Rxy1 and this is delta Rxy2, this ratio of this change is also about the same value, 2.64, around 2.8. So we have just reported that. So we do not have a very proper understanding of why this is coming from, but we have done some calculation. It looks like that the magnetization, if you consider magnetization of the state, that when it changes and the ratio gives around the same value, about 3.5 value. So our numbers are not too off from this. So it's very interesting. So it looks like, so that's how we solve this problem. We believe that these ferromagnetic and antiferromagnetic competing interactions, these are kind of intrinsic to this, and therefore the ground state of the bulk system is ferromagnetic, which our calculation also shows, measurement also shows. But if it is in the monolayer stage, and if this is a very clean sample, one can possibly figure out that there is a competition between this ferromagnetic and antiferromagnetic state. All right, so then we try to also look at, in these kind of systems, one can look at if you can tune the interactions. As I mentioned earlier, that in the two-dimensional materials, the interface can be very clean, and in a very clean environment, you can perform you can have the samples and understand their behavior by performing certain experiments. So we try to look at also the tunability of these. So one of these work that we did is on the same system, right? But then we put graphene on top of that and made a heterostructure of this. So this is a literature result. They had shown that they see certain kind of, with this material, with graphene, they see certain kind of behavior. Uh, but it was not clear what this is exactly. So they said this may be skyrmions because they have not measured it. And they have shown that without graphene, this hysteresis is like this, and with graphene, the hysteresis is like this, right? So they said that this is possibly topological Hall effect, and now you should have some idea that how it looks like, and that's how they have reported this figure, this work. So we try to look at that in detail. So this is our sample, iron germanium telluride, in the border is in red, and then graphene, which is in black. Right, and yeah, we have performed these measurements, and you see that now the hysteresis loop is very different, and that tells us immediately that we are able to actually tune the interactions. The results look pretty clean. And then we try to do the measurements of this, because our intention was to look at the chirality. By the way, the graphene has a very low spin orbit coupling, but here we believe that because of special spin orbit coupling, I do not have time to discuss this, but it's coming from the interface, right? So it's called Rashba type spin orbit coupling, and because of that, there is a Zelensky-Moria interaction, which leads to some magnetic skyrmion. So we have just measured that with the Lorentz transmission microscopy with Argonne National Lab. So this is these are the magnetic skyrmions in those samples in the two-dimensional materials, van der Waals materials that we are fabricating. So here, this is just to show that our bare sample was like this, and then with with the other heterostructure sample, like which is graphene in this case, the hysteresis loop has become like this, and this shows that these are some magnetic skyrmions in this system. Right, and these are also Niels Kerman. One can identify from the figure. So this is a Lorentz transmission electron microscope image again. Right, for the if this is a Bloch fermions, the image looks like behaves like this. If this is a Niels fermion, then the image looks like this. So our image is like this. So this we confirm that these are kind of Niels fermions in our sample. Okay, so this is another sample that we have targeted, right? So another high spin orbit coupled material, platinum diacylylide, again heterostructure. There also we do the measurements and we tune the interactions to some extent. And yeah, so sorry, I've taken it from a different talk. There is no poster, of course, but the hysteresis loop has changed here, and we also see magnetic skyrmions in this case measured at 100 Kelvin and yeah, around 130 sorry, 100 millitesla field in this case. Um, we have fabricated a sample where both platinum diacylylide and graphene covered samples. So one side, this side is graphene, this side is platinum diacylylide, iron germanium telluride at bottom. Let me see, there is a, yeah, so we have measured as a function of field. If you can see the video, I'm not sure, as a function of field, you can see how the how the skyrmion evolves. Now it is at the saturation at 1400 millitesla. Is the video visible?
Yes, sir, it is playing.
Okay, so let me then oops.
Sir, can we
Yeah,
that video again?
yeah, I'm
Really nice to
yes, I've
watch
just
these
started.
skirmions moving or reappearing.
Yeah, I've just started. I'm restarting again. Okay, so those who are not able to follow, just so what do you so this is at a certain temperature, 100 Kelvin temperature, Lorentz transmission microscope images on our samples. Uh, as I said, on the this is on the same, the experiment was performed on the same go. So that means two samples simultaneously. One side is iron germanium telluride with platinum diacylylide covered with hexagonal boron nitride, and the other side is iron germanium telluride with graphene. For both the samples, I have shown you the transport measurements. Now I'm playing the video again, and you see that at 100 Kelvin, as a function of field, how the graphene evolves, right? So this is, yeah. Now it goes to saturation. All right, so this is field dependent, and here I think another video that I have for the temperature dependent. So you can see at a yeah, it's a temperature dependent, and above the skyrmion temperature, so the system doesn't show any kind of signal anymore. I'm playing it again. Yeah, so few different temperatures, and we are able to actually relate this image with the temperature dependent behavior of the anomalous Hall effect that we measure here. So by the way, so our signal, our Hall effect doesn't show the typical topological Hall effect that people have measured in this case. So therefore I'm just highlighting this fact that those kind of topological features that we are talking about, they may not be topological all the time. So one has to be very careful to say that those are topological Hall effect. Right here I show you that in the anomalous Hall effect we see certain features which are relevant to the magnetic skyrmions that are appearing in the system. Right. Manoj, should I take 2-3 more minutes? I just thought there is another interesting should I stop or can I take 2-3 more minutes?
सर बताइए आप अगर ओके 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 ओके
Someone is saying to continue. So if you are okay, then I'll just like to discuss about one more technique and then I'll finish it. Okay.
Yes, sir, that will be nice. Actually, there were so many terms which are new to us. So it will be really nice if we can have directly the queries regarding those things. If anything is not clear, then it is the time we can relook to those terms. There are several questions, sir. Can you read the questions from the chat
Oh,
or
I
offline
see. So,
also?
so I'm not continuing with the talk. Then I'm finishing it, right? And then we take the questions. That's what
Okay,
you're
sir.
saying.
Oh, yes, sir. Possibly we can stop here.
Stop here. Okay, fine. Fine. Okay, so let me see the. There has to be the chat box, right? Somewhere. Hmm, chat box. Okay. A lot of questions. Okay. So, so will you kind of somehow moderate it, or I read through these questions? Maybe I can start from the end or something.
Up to you, sir, as you can comfortable. So I think the very first question was something like, what is two in, two out in that
Oh,
square
yeah,
lattices?
yeah. Okay. Um, let me. My slide is still shared, right?
Yes, sir.
Okay. Okay. So maybe I show it here first. Yeah. Okay. I need the laser pointer. Hmm. All right. So, so this two in two out, that we call it ICE rule, right? So, if you let me explain it here. So water ice, right? If you consider water ice, which is H2O, right? So typical structure, if you remember from your, I think, chemistry textbook, uh, the structure is like this. So you have oxygen ion here, right? And in a water ice, two hydrogen, in a water ice lattice, two hydrogen ions are closer to this oxygen, and two are away from this. So you see this one and this one are closer to this, and these guys, they are far away from this. So therefore it is called two in and two out. Okay, in terms of the position of the protons here, and this is called ice rule, water ice. Okay, so now so it's two in two out in terms of the position of the protons with respect to the oxygen ion in a water ice, right? Now I was discussing about this kind of magnetic system, pyrochlores, where the magnetization, it's not the position, but is the orientation of the magnetization, which is pointed in a way. You see that this is one in, this is in, this is also in, right? You see the arrow head towards the tetrahedra, and this one is out, this is out. So this is again two in, two out. It has nothing to do with water ice, right? But just because the orientation is two in, two out, that's why people have termed it as kind of spin ice, right? It has nothing to do with frozen thing or anything. This is just because this water ice is two in, two out in a completely different sense. Here it is two in, two out for magnetization orientation in this pyrochlore lattice. So, yeah, so that is in the pyrochlore lattice. For artificial spin ice, again, it was found that, if you calculate, if you create this kind of structure, let's say it's a square lattice, so these are all individual magnets, nanomagnets. If you uh, create those structures, then you look at it and you see that you can calculate also the energetically. This is two in, two out. You see that this is the vertex, right? So this is in, this is in. This spins in, and these two are out. This is 2 in, 2 out. This is also T in, 2 in, 2 out. These are degenerate states, right? Of same energy, but this 2 in, 2 out is the lowest energy state, ground state. This is also 2 in, 2 out, slightly different. You see that there is more frustration in this. This one, these are in, and this one, these are out. And these are 4 degenerate states here in this case. So these are all 2 in, 2 out. Here is this one. This is, let's say, this is out, this is out, this is out, and this is in. So this is 3 in, 1 out. So something like, so similarly, 3 out, 1 in, these are all degenerate state, right, of higher energy. Then higher energy, then type 2 and type 1. It's 5 o'clock. So type 4 is the highest energy state, all in or all out. I hope this is clear now.
Yes, sir.
Okay.
So the next question is from Bhavna Mahesh. In spin liquids, what forms a qubit?
Oh, yeah, I have not discussed that. So you see that for the qubits, these are, I mean, only thing that I wanted to refer to here is that there is an entanglement. I think I clarified a little bit in details, that under this existing model, this resonating valence bond model, right? So there is an entanglement between the two spins sitting at the triangular lattice, right? So this, for qubit, if you have little bit of ideas, so this quantum entanglement is important for those quantum computation, and that's what I referred to. That's what I meant, that this is how it is relevant to this quantum computing. These are spins entangled, long range entanglement. These are the two cases that I have shown, that is the nearest neighbor entanglement between the two spins, antiferromagnetically coupled, and there can be also long range entanglement. Entanglement in this system is, if these are found, these quantum spin liquids are found, then these are automatically candidate for the quantum computing.
Okay, sir. Okay. I think Lakshmi Narasimha Rao, he said a few of the jargons are new. Actually, this is the first talk where we are having uh, experimental things on directly on the quantum materials. So far, we have been going through the basic condensed matter or solid state physics type of lectures. So there are few new things coming up, and as sir also mentioned at the beginning of the talk itself, that there are several class of quantum materials, and we will cover those classes in different lectures. So possibly, I think we will get habituated to these terms. But if there is anything specific which is not clear yet, then I would like to ask Dr. Lakshmi Narasimha Rao to please mention in the chat the terms which were not clear. So the next question, I think you probably maybe addressed already. Is there any signature of Skyrmians in transport measurements?
Yeah, I think I have covered that, right?
Uh,
So this is a topological Hall effect people talk about, but as I try to warn that this is not the kind of settled issue in the community, right? When the topological Hall effect was first measured, there was a lot of excitement, but it turns out that now several theories are coming up showing that under also different kind of configurations, spin configurations, one can get those kind of features, which may have nothing to do with skyrmions in the system. So
oh,
okay, so one has to be a little bit careful at this stage.
so just by looking at this these signature, we cannot be sure that they can be
Just
from
just looking at
Skyrmians.
the topology way, the way it was like when the topological Hall effect was kind of reported for skyrmions, then people started looking at many different crystals, many different materials, and whenever they found this kind of Hall effect signature, people just said that there are skyrmions in this. This is a candidate for skyrmions. That was the problem because theoretically, also experimentally, people have not shown that there are skyrmions on those samples. They have just shown that these are kind of transport signature. Theoretically also it is not settled. Theoretically it now turns out that there are many other there are few different cases where very similar kind of behavior can be found, can be observed, so which may have nothing to do with any topology or and any topological texture in the underlying lattice, magnetic lattice. So therefore one has to be a little bit careful.
Okay, sir. So then the next question, I think this is the repeated one. What is two in, two out in lattice? That is clear already. Sir, kindly discuss on Skyrmion dynamics and also one more query that I'm assuming the slides will be shared in some reading materials. So yes, sir. There were so many new things coming up. If you can share some study material along with the slides, that will be really useful. So I would like to request you to suggest some literature so that these topics may be further studied by the participants.
All right, all right. So just only one thing, I'll be actually traveling to US tomorrow. A little bit difficult immediately to do something, but maybe after I return, so around after 25th, I should be able to do it. I hope that that should be all right. In case I can
Yes,
manage.
we will be still there. So yes.
Yeah.
So can you want to discuss something on Skyrmion? I think you already discussed those dynamics of involving Skyrmion. Anything more to add?
Uh, yeah, dynamics. I do not know what dynamics you are interested in to discuss. I didn't. No, I didn't include the dynamics. See, there are high frequency dynamics, some different kind of modes of oscillations of those fermions. I'm not an expert on that. We do not work on those areas, but we do look at low frequency fluctuations. I mean, I can just make one comment possibly. Um, the people have observed these skyrmions. So what I talked about mostly the static skyrmions, but these skyrmions are skyrmions at room temperature. People have found observed that they are kind of diffusion, Brownian motion of the skyrmions. They diffuse in the system. So there are some kind of dynamics, but yeah, so the exact behavior is not very clear yet. We are interested in those kind of measurements. We are doing some measurements also for fluctuations and looking at those things, but it's extremely difficult at this stage, so I do not have much comment on those. But yeah, so most of the dynamics people looked at, actually these are kind of skyrmions at very high frequencies, and there are kind of different kind of breathing mode, different kind of modes of oscillations in gigahertz frequency range. So I've not followed that work, so right now actually I'll not be able to discuss in details about those dynamics.
Okay, sir. This is a really very interesting topic, it seems. By the way, I just want to add that there will be another talk by Professor Ajit Patra on chains. So possibly he can also add some more information on Skyrmion. And I would convey that if he can include the Skyrmion dynamics,
Yeah, maybe we can include that, right? Yeah.
yeah, then it will be better.
Yeah, I have not planned it that way actually. Yeah.
Yes, sir. Yes, sir. Okay, sir. So the next thing, next question or query is how much research work going on India in this? Any company working in this product development? Mm, which type of product development? It is not yet clear, but possibly some involving some magnetic quantum materials, I suppose, sir.
Yeah, so in the Skyrmion physics, typically the physics which require very high quality materials. So there are very few groups in the world actually who can grow extremely high quality materials, and they have started quite long back. In India, there are only very few groups who are working on this, but as it is always. When you start something new, you need to reach to certain level of maturity before you go to the application level. The Skyrmions, when it started, there was a lot of excitement about the application in magnetic memory, based on the magnetic skyrmions. So there, before the skyrmions, there was an idea of IBM research lab about domain wall based magnetic memory, typically called race take memory, which should be low cost memory, relevant for the modern computing and everything. But then when the skyrmions came, there was a lot of excitement. But yeah, so there are a lot of issues which is still to be solved. And right now, from the application point of view, people are looking at other aspects like skyrmion based logic, skyrmion based sensing, quantum sensing, skyrmion based neuromorphic computing, etc. Those kind of things. Not too much into the memory. And I believe that in India, those kind of applied research, yeah, it's a little bit far away because it's still not matured enough to create those kind of materials. So what you see here, what I've shown here, they are extremely high quality materials and require quite a lot of I mean, there are some groups who are doing this. We are also working. I'm not into the material, but we are doing a lot of measurements, try to understand the basic physics in this. Yeah, but application wise, I think in India we are not yet there in the skyrmions. It will take a while. Yeah. And the other thing is that every once in a while there are new materials, new physics come up, and people move to different areas and things like that, right? So that's also another issue. Mm.
Yes, sir, that is sure that this type of physics can only be seen in very clean systems, perfect samples, and sample synthesis takes time, and also, as you mentioned, it it has to be uh, done over the years, maybe possibly for optimization and all. So the next query can is, if one finds berry phase in K space, isn't mean that it also present in real space.
No. Uh, Serial space, this is a typical example of the very phase in kind of. So the idea is that you have to have um, uh, adiabatic um adiabatic process in this. All right. So in these fermions, at least this is what the understanding is. As I said, the topological Hall effect is still under a lot of investigation. But as far as the current theory is concerned, the the very phase in the local space, real space, comes because of the texture that we have. So if the electron moves through these fermions, its spins get oriented due to the exchange interaction with the local spins of the fermions, and it goes through a complete cycle of this. And that's what I tried to show, that it is a cyclic process. If this moves adiabatically, then this is an extra component that that this electron acquires in this case. So yeah, so if it is in the K space, it doesn't always mean that there will be also in the real space. So K space very phase gives you anomalous Hall effect.
Okay, sir. Uh, so there are some requests to share some study material related to these things. And then schedule of talks. This is for us. I have already shared the schedule, updated schedule with the participants again. Sir, is it possible to measure transport of topological surface states theoretically?
Theoretically, you calculate, right? Theoretically, you don't measure. So, uh, yeah, I think, yeah, I think I'm not a theoretician, but the theoreticians look at the transport behavior of the topological
Mm.
states. Yeah, but exact details they will be able to tell you.
Yes, sir. Yes, sir. So we'll have talk on the
Yes.
topological material uh, by uh, Professor Bahadur Singh from TIFR.
Hmm.
So possibly he can address this query uh, later. And sir, do IIT Delhi teams work with Microsoft on topological qubits? Hmm.
Um, no, not yet.
Okay, sir. How the Skyrmion historic properties can be useful for quantum memory?
Oh, okay. It is not the, so what I mentioned is not about the, you mean possibly hysteresis, right?
Yes, sir.
Yes,
Looks like.
Prahlad Rao. Yeah, it is not about the hysteresis. This is about the motion. I mean, yeah, in some extent, in a way, this is the dynamics of skyrmions. So dynamics means is basically motion of skyrmion through certain track, right? So you can fabricate certain you call it a race track, right? The race track where you basically run on the ground, the athletes run in a one way. You define predefine the track and then the athlete runs, right? So this way you can create some kind of nanostructures, nano track, and there is a way to move the skyrmions in a controlled way. I have not discussed those things. So you can actually apply some current pulses and then move the skyrmions. So people look at actually the velocities of the skyrmions of these things. So so basically the memory means in this case that important point is that, you know, if you remember, I showed you a video at the beginning when I started, right? So this is a soliton. So soliton means it's kind of a particle. It's a solitary wave, and it behaves like a particle because you know, it moves without being destroyed for large distance. So similarly, this fermion, this is a topologically stable, you know, kind of quasi-particle, particle-like entity, right? So it would move without being destroyed. So there are many magnetic states, for example, domain walls. If they find a defect, for example, they will get destroyed. So for skyrmions, it is extremely hard to destroy it. So that means when it moves through this racetrack, if you can move it in a controlled way, then one can consider that, okay, so in a certain point, if you can, let's say if you have your read device, if your reading device, okay, so you can consider that, okay, if I have a skyrmion at my reading or close to my reading device, this is my memory 1. If I do not have a skyrmion, I have a 0. Okay, so that's how you can use it as a memory, just by moving this. Okay, so either you, presence of a skyrmion, you consider it as 1, absence of a skyrmion, if you move it, and it's a 0. So that's how you can use it as a memory for your you know, for your work. So that's what I meant.
Yes, sir. Actually, he has added new comment like earlier we know this ferromagnetic hysteresis is used for magnetic materials, and I think as you mentioned also already, that people have tried to make magnetic memory devices out of skyrmions. May not be quantum memory, but there were trials, I think.
Yeah, so with the Scalmion, this is the racetrack memory. So I think what he is talking about in general, you know, the magnets can always be treated as a memory element, right? Because
Yeah.
typically for any memory element, a solid state based memory element, you need a power to, you know, keep it running, right? So for a magnet, it's just magnetization, switching one side to the other. So if you can use it in a proper way, in a clever way, then you can use it as a memory. So only thing is, I mean, this all these if you look at the earlier IBM hard disk and everything, these are kind of ring shaped magnetic memories. Okay, so you can't you can change the magnetization, then you can take one magnet as a memory, but the issue is that you want to target individual magnets, right? Because you can't have 1,000 magnets all affected by an external field. No, so there is yeah um, so that there are wires, current, leads going through those kind of rings, and then magnetic field, you just pass a current through one ring, so that only that ring is affected. So there you write it, you need to write, you need to read, so those things you have need to take care of. So the initial stages, those are of course all the magnetic hysteresis based memories.
Yes, sir. That was the last query, and it was really very curious talk. I also came to know several new terms and development in this class of material. And it is always good to hear you, sir. I mean, so thank you once again.
Yeah, thank you very much. I just tried to keep it a little bit. I didn't try to go too much into details because I thought the idea would be to give a little bit of overview to the audience about few of the materials, because the topic is kind of magnetic quantum materials. So I didn't purposefully I didn't touch upon any topological magnetic materials, because as I said, I think someone else will take care of that. And within 1 hour, I think this is what was possible. So thank you very much.
Yeah, exactly, sir. Thank you. It was the best utilized time, and we have in line 4 or 5 more talks on magnetism in quantum materials. So many other aspects will be
Covered.
covered in those talks.
Yeah, sure.
Yeah, yeah. It was really nice, sir. Thank you so
Thank you. Thank you
so
very
much.
much. Thank you.
Okay.
Okay. Yeah. So I'll
Bye, sir.
log out. Huh? I'll log out.
Yes, sir. Please.
Okay. Thanks. Mhm.